Okay, engineers, on this video we are going to see how to get the Laplace transform of periodic functions. First of all, what is a periodic function? Well, a periodic function is a function that actually repeats itself certain amount of time. Okay. So, for instance, this is a seesaw function where it goes up and then drops, goes up and drops, and so on. So, the first thing to mention here is how much is the time to repeat itself. So here for this is the period of t, capital T. So capital T is period. It's a very important thing to remember. The period of time to repeat the function itself. Now, so what happens here is in mathematically, a periodic function is a function that you shifted plus t or minus t, exactly this, the period is going to be equal to the same function, right? So if you graph the function and you displace it to the left or to the right, exactly equal to one of the periods, then if you do that, if you shift it, there will be a time where you are going to overlap the same function, right? To the right. Now, if that overlap happens when you get the period of t. So a shift to the right or to the left is equal, it repeats itself the function. So this is a periodic function mathematically. Okay, now what we are going to do right now is try to get the Laplace transform of periodic functions. I usually write the periodic function as so index capital T. Okay, by definition, we are going to write this by definition. By definition is going to be the integral from 0 to infinity exponential minus st, the periodic function. Well, that doesn't tell me much, but let's do this. On this example, I'm going to split the integral in two integrals. The integral from 0 to the first period, and then from the period to the infinite. So what I'm going to do is the integral from 0 to t, exponential minus st, periodic function, differential of t, and then plus the integral from the period of t to the infinite, exponential minus st, periodic function of t, differential of t. So it's actually the same integral. Here is from 0 to infinite, and here is from 0 to the first period, and then from the first period to the infinite. So it's actually the same integral. I want to focus on this one. I'm going to do a variable change. A variable change is going to be something like this. It's going to be, let's do w equal to t plus capital T. Okay. I hope that is the variable change. Now maybe it is going to be no, it's going to be t equal to w plus the capital T. Okay. Now differential of t is equal to differential of w. The period of t is constant, it's a fixed number, it doesn't change in time, alright? And then the w is actually t minus capital T, alright? Okay, so let's do the replacement. On the first one, this first integral, we don't change anything. What we are going to change is the second integral. So I'm going to rewrite the first integral from 0 to capital T, expansion minus st, the periodic function of t, differential of t, plus the integral. Now let's do the variable change here. Exponential minus st, but t is w plus capital T. And then f of t, but t is actually w plus capital T. Differential of t is going to be differential of w. Now, be careful because you have to change also the intervals. Okay. Now, this is t equal to capital T, and this is t equal to infinite. Now, this integral is in w. So, what is the value, the initial value of w, and what is the end value of w? Okay. So, when t is equal to t, so how much is the value of w? If you replace the value of capital T here, t minus t, capital T, is going to be 0. And then if you replace the value of infinite, infinite minus one period is still infinite, so it's going to be infinite here. Okay, so let's continue. Integral from 0 to capital T, exponential minus st, f of t, differential of t, plus, now this is the integral from 0 to infinite, exponential minus sw times exponential minus s capital T. If you multiply this times this and this times this, f of tw plus capital T, differential of w. I'm going to make a variable change here. I'm going to change w equal to t. And now we can actually, this is capital T, we can take outside this this exponential. Okay, so this is equal to the integral from 0 to capital T, exponential minus st, the periodic function differential t plus exponential of minus s capital T, integral from 0 to infinite, w equal to t, exponential minus st. Alright, now this is outside, and this is f of t, t plus capital T, differential of t. Now, this, have you seen this before? Well, is this part, f of t plus 1 exactly period is equal to the same function. So this is actually, we can replace this by simple f of t. Alright, now from where this comes from? Well, it comes from here, well, from the Laplace transform of the periodic function. Now from here, so this is equal to integral from 0 to infinite, exponential minus st, the periodic function of t, differential of t. Now you can see here that this number and this number, they are actually the same. It's actually the Laplace transform of the periodic function. So what we are going to do here is pass this to the other side, factorize it, and clear this. So if we do that, it's going to be the integral from 0 to infinite, exponential minus st, the periodic function of t, differential of t, is equal to, if we pass this to the other side, it's going to be, this integral is the same, integral from 0 to infinite, no, integral from 0 to capital T, exponential minus st, the periodic function of t, differential of t, and here the division. Now this is the interesting thing. This to the other side is going to be 1 minus this, 1 minus exponential minus s capital D. Okay, so what we got here is, from here this comes from the Laplace transform of the periodic function. So this is the formula to calculate the Laplace transform of periodic functions. Alright? Okay, now let's do one quick example, example of this formula. Let me erase this part. So I'm going to erase this part because what I want is the formula. Okay. You may already know periodic functions. Alright? So let's do one test of one periodic function that you already know. Okay, so let's do the Laplace transform of the sine of t. You already know the answer is actually 1 over x squared plus 1, but it turns out that the sine of t is a periodic function. It repeats itself every 2 pi. So that is a period, right? Capital T. Okay, so that is the period. Now, let's see if we use this formula, we should get the same answer. Okay, let's try it. If we use this formula, then it's going to be 1 minus exponential of minus s, the period of t, capital T, is equal to 2 pi. And here is the integral from 0 to 2 pi, from 0 to 2 pi, exponential minus st, the periodic function, the sine of t, differential of t. Okay, now I'm going to solve the integral here and then plug in later. I'm going to erase this part because I need it. And we should get 1 over s squared plus 1. Okay, so the integral from 0 to 2 pi exponential minus st, the sine of t, differential t. Now, I'm not going to use two integration by parts. Instead, I'm going to use a formula. The formula goes like this: exponential minus st over a squared plus b squared, s squared plus 1 squared. I'm using the formula integral from 0 to integral of exponential of at sine of bt differential t, and that is equal to exponential of at over a squared plus b squared, and then here is going to be, I have to check this, it's going to be a cosine of bt minus b sine of bt. Let me check this formula very quickly. Okay, the sine is going to be a, no sorry, here is sine pt minus b cosine of bt, sorry, cosine. Okay, I'm using this formula. In this case, a happens to be minus s and b happens to be just 1, so that is why a squared plus b squared is s squared plus 1, and here minus st, and then here is going to be a happens to be minus s sine of t minus the cosine of t, but still we have to evaluate this from 0 to 2 pi. Okay, I'm going to erase the formula. I'm going to erase the formula and let's do the evaluation. So, the upper limit, exponential minus s to pi over s squared plus 1, and then here minus s sine of 2 pi minus the cosine of 2 pi. That is the upper limit minus the lower limit, exponential minus s0 over s squared plus 1, and then 0 is going to be minus s sine of 0 minus the cosine of 0. Okay, the sine of 2 pi is actually 0, the cosine of 2 pi is actually 1. Sine of 0 is 0 and cosine of 0 is 1. Okay? Okay, so it's going to be exponential minus 2 pi s over s squared plus 1, and this is minus 1, and then minus times minus positive plus exponential of 0 is just 1 over s squared plus 1. So we have the common denominator, s squared plus 1, in the numerator is going to be 1 minus exponential minus 2 pi s. Okay, we have solved the integral. Okay, the result of the integral is this. Okay, now let's plug in the formula. So this divided by this, so the Laplace transform of the sine of t is equal to, the result of the integral is this, 1 minus exponential minus 2 pi s divided by s squared plus 1, and then divided by 1 minus exponential minus 2 pi s. As you can see here, this number and this number, they are the same. So if we apply the sandwich rule, this and this cancels. So the only thing left is 1 over s squared plus 1, which is what we expected because it's the Laplace transform of the sine of t. But this shows that actually the formula works. Now the formula that we proved here works to find the Laplace transform of periodic functions. Okay, on the homework you have to solve one or two periodic functions. All right. Okay, with this we finish the unit. See you soon.